Hello and welcome. Today we're gonna look at contour integration, and we're gonna look at two special integrals. They're known as the Fresnel integrals. Um, they they have exactly the same value. That's the integral from not to infinity the sine of x squared, or if we replace in the argument the cos of x squared, the answer is exactly equal to the square root of pi over 8. And the contour integration that we're going to use for this particular one is not the most straightforward one. You just need to have seen a couple of things before and use a couple of other results, such as the Jordan's inequality, as well as the Gaussian integral result, which we're going to quote, of course. So let's start first of all by picking an appropriate contour for this, and the contour is not obvious at all. The reason I know this is the one is because I've seen it before. So real Z, and this is im Z. And the contour that we need for something like this is a sector centered at the origin and subtending an angle pi over 4 at the origin. Okay, so this is our gamma. So let's label it appropriately. So this is big gamma traced in an anti-clockwise direction, radius r, and probably be better to split it into three: gamma 1, gamma 2, and gamma 3 in terms of labeling. Of course, we'll split it into three, but label it separately so we know where we are. And we're going to start with this particular integral now, section by section. So we're going to say, okay, if we integrate around gamma f of z dz by the residue theorem, the answer is going to be, of course, 2 pi I times the sum of the residues inside gamma. But we notice that this particular function that we're going to pick, in fact I haven't actually picked it up, so let me just say what my f of z is going to be for something like that, because I'm trying to actually get both of them in one go. So this is going to be gamma e to the I z squared dz. We notice our f of z, okay, has no poles inside gamma, and therefore the answer to this particular integral must be 0. Because they think there's no residue, so times 0, or by Cauchy's theorem, the answer is still 0. Okay, so our next line, as per usual in this kind of work, we're going to say, you know what, the integral around gamma 1 plus around gamma 2 plus around gamma 3, curly bracket, f of z dz, in this particular case, will be 0. So we're hoping that our integrals are going to come from the straight line segments that we got in here, and the contribution of around gamma 2 in the limiting case as r tends to infinity, of course, is going to be 0. So let's start with what we're hoping that will have a 0 contribution, which is the integral around gamma 2. So let's start with gamma 2. Around gamma 2, z is equal to r e to the I theta. R dz is, of course, IR e to the I theta d theta, and it runs from 0 to pi over 4. So all good, all straightforward stuff. So let's do this estimation. So the integral around gamma 2 f of z dz is equal to, parameterize it, 0 to pi over 4. Now e to the I z squared, be very careful, it's very messy. E to the I z squared r squared e to the 2I theta, pardon me, and our dz is IR e to the I theta d theta. Close the mod, standard stuff, less or equal to, move the modulus inside there, integral, so 0 to pi over 4. Rewrite it also a little bit. So let's write some of this stuff first. So we're having I r e to the I theta, that's this bit here. And then that's an exponential within an exponential total mass, as we can see, I r squared e to the 2I theta d theta. And this is what we got in there. Let's move that a little bit further. Okay, luckily we have 4 multiplicative quantities. So what we can say there is, now split that into 4 moduli. And what are we going to get if we continue with this particular one now? The modulus of I is of course 1. Okay, so we're having 1. The modulus of R is simply R. So we can actually write outside the integral in this particular, on this particular example. So we got R, and then we got e to the I real, which of course is equal to 1. And all we got inside the integral is 0 to pi over 4 e to the I r squared e to the 2I theta. Oops, that should be integral sign there, d theta inside a modulus. Now what do we do from there? I mean, we have an integral within an, sorry, not an integral, we're having an exponential within an exponential, total and utter mess. It might make sense now to perhaps switch into sines and cosines. So this is going to be equal to r integral 0 to pi over 4. And this will now give us I r squared, that's up to here. And this now is going to be equal to cos 2 theta plus I sine 2 theta. And then we've got, of course, d theta. And we can split the exponential. So we can actually write it for simplicity as 0 to pi over 4 e to the I r squared cos 2 theta times e. I times I is minus 1, so that's going to be a minus r squared sine of 2 theta d theta, still under the modulus. And of course we have a multiplication here, which is rather nice. So that means the modulus can take this form. And again, that's very nice because of course that's e to the I real modded, which of course is just 1. So the only thing that we got in here now is r 0 to pi over 4, and we have e to the minus r squared sine 2 theta d theta. We don't actually need the modulus for this particular one. This is going to be now a positive quantity on this particular range, and it's all fine. We can just throw the modulus away. Now, how do we make progress from here? Now, the way we make progress from here is by using Jordan's inequality. I'm going to quote it here. You can look it up, you can Google it. Jordan's inequality is used in the proof of Jordan's lemma. Inequality. And this is what it says. It says that let me just write it first of all. It says if theta is between 0 and pi over 2 for acute angles, if you want, then this particular inequality, this is two inequalities combined into one, is actually true. So somehow we need to, the rationale behind all of this is to replace the sine of 2 theta via this inequality to something that just has theta, in which case we'll be able to integrate it. So first of all, we have a sine of 2 theta. So the obvious thing to do is in the inequality is to replace theta for 2 theta. That doesn't affect the end point, so it's going to be 2, but it will affect this bit here. 2 over pi. So we got the sine of 2 theta over 2 theta is less or equal to 1, but now the inequality is of course between 0 and pi over 4. So now we need to see which of the two inequalities that are combining there we need. So somehow, in order, because you remember we're doing an estimation, less or equal, so we don't all of a sudden, if we stick there a greater or equal, we got a problem. So we need to have it like this. So let me just write it first of all, and then I'll see which side of the inequality we're after, pi over 4. So we want to make sure that the integrand is actually larger. So in this particular case, so this is less than that, so we need this side. So let me explain. So first of all, theta is between 0 and pi over 4. Is fine to multiply across in the inequality. So the sine of 2 theta is greater or equal to 4 theta over pi. And if we put now, because this is going to be larger, and we have the minus in there, the inequality at the front will be the other way around. So we can actually, so our claim we have here is the r at the front, e to the minus r squared, and the sine of 2 theta has been replaced with 4 theta over pi. And from here we can actually integrate that. That's going to now equal to, and what do we get for this? Is the integration? Oh, oops, I forgot the d theta there, sorry. So we got r. Let's put the limits is with respect to theta, so it's going to be a minus, this is flipped upside down, a pi, a 4 r squared, and e to the minus 4 r squared theta over pi, 0 to pi over 4. What happens next? I don't like this minus in here, so what I will do is I will first of all multiply that out. So it's going to be a the minus I'm going to use to reverse the limit, so it's going to be a pi from there, and at the bottom I've got 4r. The other r has cancelled. I hope I haven't made any omissions or mistakes in there, and because I'm reversing the limits, this minus has now gone, so it's going to be e to the minus 4r squared over pi theta, and that's from theta is equal to pi over 4 to theta is equal to 0, so it's going to be pi over 4r. At the front, I'm going to put 0 for my theta, this is going to be equal to 1, and when I put pi over 4 is going to be minus e to the minus r squared. And what happens to this as r tends to infinity? This definitely goes to 0. First of all, e to the minus r squared will definitely go to 0. So the dominant term of the bracket is this 1. And of course, that's of the order 1 over r. And therefore, this tends to 0 as r tends to infinity. So as perhaps we expected, the contribution around the curved bit around the semicircular arc has 0 contribution, so we can concentrate now on the straight line segments. So I'm going to make some space, so we need to leave that in there. The rest is not really needed. So we're going to parameterize the straight line segments along gamma 1 and along gamma 2, and hopefully get our answer very, very quickly. I think the estimation, it was actually the longest bit in this particular integral. Okay, so we're ready to do that. Let me actually let's rub off the this information about gamma 2, and let's put information about gamma 1 now, and about gamma 3. So around gamma 1, z is simply x, or if you prefer, x e to the 0 I, the dz is simply dx. And the limits go from 0 to infinity, as we looking at the limiting case. Around gamma 3, z is equal to x, but it's not as simply z is equal to x, it's z e to the I pi over 4. I'll probably leave it like that, so I'm going to get my dz. My dz is equal to e to the I pi over 4 dx, and the limits come from infinity for this one to 0. So I have to be a little bit careful now. So this is what we got so far. And of course, this in the limiting case, as r tends to infinity, that has gone. So if that plus that is equal to 0. So what do we have? We look at the gamma 1 first of all. So we're having 0 to infinity, e to the I z squared, so e to the I x squared dx, plus, now we're looking at the gamma 3. Gamma 3 now comes from infinity to 0, first of all, and is e to the I. What is z squared? Z squared is going to be x squared e to the I pi over 2, and the dz there is going to be e to the I pi over 4 dx, and the answer to that is 0. Okay, it looks a bit messy, but it's not that bad. For this one, we're going to switch into sines and cosines. So let's just do that straight away. Let's leave it for one more line, because I want to do a bit of a tidy here, so it's less to write on this. So not to infinity, e to the I x squared dx, plus, first of all, e to the I pi over 2 modulus 1 argument pi over 2, that's simply I. And now I've got another I at the front here, so that's an I here. I times I is minus 1, so it's going to be e to the minus x squared. And this particular quantity is modulus 1. Let me write at the front. So first of all, the limits, I'm going to, actually no, what I'm going to do with the limits, I'm going to flip them and move them to the other side. And here I have e to the I pi over 4. Let's just double check that everything is there. First of all, I moved that to the other side and I swapped the limits. So the limits now are not to infinity. Okay, so that's took care of this quantity here. This is going to be an I times I is minus, that's e to the minus x squared. So that's this bit here. And e to the I pi over 4 is a constant, and I moved on the other side. Sounds okay to me. It doesn't look like I made any errors in there. So the last line from here now is to say, you know what? I'm going to switch into sines and cosines this bit here and compare real and imaginary parts. So this is going to be the cos of x squared plus I sine of x squared dx. Now e to the I pi over 4 is, of course, let me just write it in full. It's going to be the cos of pi over 4 plus I sine of pi over 4. That's this bit here. And of course, this is a very famous integral whose answer is the square root of pi divided by 2. This is known as the Gaussian integral. I've already done a lecture on that, so it's already, I can't remember, it's quite a while back now, but you can actually look for it. It's the integral from minus infinity to infinity of e to the minus x squared dx is equal to the square root of pi, and because we have an even integrand, from naught to infinity is exactly half of it. So what does that give us? Well, does that give us now a root 2 over 2? It might be a better idea to write it as 1 over root 2 plus I 1 over root 2 as well, multiplying the square root of pi over 2, and probably I'll write as the square root of 4 because of how I have the answer up there, and therefore the final answer for this particular one, not to infinity, cos of x squared plus I sine of x squared dx is going to be equal to square root of pi over 8 plus I square root of pi over 8 as required. Not a very lengthy integral to do with contour integration. The estimation wasn't really that bad, but it did involve the Jordan's inequality, and of course we have to use this result. We cannot sort of like go and say, well, we don't know what once we reach this particular stage, but this has a collection of very important results from higher level mathematics, and I hope you enjoyed it, and I hope you learned an awful lot from it, and for the time being I will be signing out, and I'll be seeing you very, very soon. Bye for now.